Next educational video, local extrema. In this video, we will learn how to find the so-called local maximum or local minimum for function of two variables. First, let's look at the definition. Local maximum. F is said to have a local maximum at the point AB if this condition holds. The value of the function at AB is greater than or equal to the value of the function at all other points in some subdomain. Here's a diagram to illustrate this definition. Let's focus on the point P and the subdomain E. Over this subdomain E, P is the highest point. So this condition holds over the set E. But P is not necessarily the highest point over the entire domain. As you can see on this diagram, Q is a point higher than P. So that's the concept of local maximum. It is a maximum only over a smaller domain, not necessarily the entire one. The same applies to local minimum. In this illustration, P is a local minimum over the set E, but not the entire domain, because Q is lower than P. So that's the geometrical meaning of local maximum and local minimum. Now let's find out how we can locate them. It turns out that all we have to do is to solve a pair of equations, setting the first order partial derivatives to 0. To understand why, let's take a front view of the zx axis for this surface with a local max at P. Taking a front view at zx axis, we can see a curve with a local maximum at the same point. But this cross-sectional curve is plotted on the zx axis. So the derivative of this curve is fx, the first order partial derivative with respect to x. This is something we have learned in the video on first order partial derivative. The same goes to zy plane. If you take a front view of the zy plane, you see a curve with a local maximum at the same point. And that's the reason why we set both partial derivatives to 0. Because at the turning point, the derivative is 0. Similarly, for local minimum, depending on how you see it, you have partial derivative equal to 0 for both x and y. It turns out that any point AB satisfying that pair of equations is called a critical point. So this is a definition of a critical point. And a critical point can either be a local maximum, a local minimum, or neither. In the third case, we call the point a saddle point. Here's a typical example of a surface having a saddle point. Let's focus on this particular point. If you take a front view of the zy axis, you see a local minimum. But if you take a front view of the zx axis, you see a local maximum. So that's the reason why it's a saddle point, because it's neither maximum nor minimum. Let's end the video with a derivative test that we can use to determine the nature of a critical point. It turns out that it's all at the mercy of two quantities. First is fxx, the second order partial derivative of f with respect to x. And the other quantity is given by this expression. All we have to do is to evaluate these two expressions at the point we are testing for the nature. And all we have to do is to look at the signs of these two quantities, positive or negative. Different combinations will lead to different conclusions. One unfortunate case is when D is equal to 0. In this case, no conclusion can be made. In a separate video, I will show you some numerical examples.